Let's review sequences. So a number sequence is a domain of a set of natural or counting numbers, which are just the 1, 2, 3, etc. Range are going to be the values of the real numbers, and there's the kind of the fancy notation for it. A1, A2, etc. are the terms. The subscripts 1, 2, 3 are the indices. You could use A, pretty much any letter except N. We will use A, S, T. We also see B, C, D, etc. All right, so some of the notation. When we say A sub n, we're talking about the nth term or the rule of the sequence. You'll see it as A sub n equals a brace 1 over n. So it's saying a sequence with the nth term of 1 over n. You may see it like this. You may see it like this, where it's saying we're going to infinity. And you just kind of get used to doing it. Write the first 3 terms of this sequence. So we have, we'll just say b1 equals -1 to the 1, 1/2 to the 1 minus 1. So you get -1. B2, -1 squared, 1/2 to the 2 minus 1. So we'll get 1/2. B sub 3 would be -1 cubed, -1 to the 2 minus 1. So we get -1/4. And if we write this out, and I'm going to write a few more terms, we have -1, 1/2, -1/4, and we just kind of continue following the pattern, 1/8, -1/16, and that's going to continue saying that positive and negative in the sequence. Since this oscillates, between positive and negative, and it doesn't matter if it's positive, negative, or negative, positive, this is called an alternating sequence. So we're going to need to know that. We're going to be dealing with that in a little bit. All right, this next part should be really easy. Just write it down to review this idea. So I'm going to show you 2 ways to find the nth term of this. I want you to be able to just look at this and be able to state what the nth term is without in simplified form. So if we look at this, we're adding 5 every single time. We could say that this is 4 plus 5. We could say this is 9 plus 5, but 9 is the same as the 4 plus 5. So we have 4 plus 5 plus 5, or in other words, we're starting with the 4 and we're adding 2 5s. Similarly, we could say the 19 would be the 14 plus 5, or 4 plus 5 plus 5 plus another one. So we'll have 4 plus 3 times 5. If we go backwards, we can fill it in. And this would have to be 4 plus 0 times 5. This would be more along the lines of what you did in previous courses in terms of writing the formula. So we'd have t sub n, the nth term, is going to be 4 plus 5 times n minus 1. But if you realize this is called a linear sequence, it's also called an arithmetic sequence. So if we are looking at this and we realize, okay, this is the first, second, third, fourth term, etc., that a linear sequence is just a line. The common difference is our slope. The 0th term, we don't start at 0, but we're going to talk about that. 0th term is our y-intercept. So since we're adding 5 going this way, we will subtract 5 going that way. So our 0th term is -1, and our formula would then be 5n minus 1. All right, next one, we have 6, 18, etc. So we look at this and say, oh, that's just multiplied by 3 every single time. So then we realize that we could set up a table like this, but you should be able to do it without it. What we're going to do is multiply by 3 on every term except the first one. So our t sub n will be 6 times 3 to the n minus 1. And this is a geometric sequence. All right, next page. Take a look at this. What's the next term of the sequence? If you're looking and you just say, okay, I'm going to follow this pattern, I'm multiplying by 1/2 every single time, this is 1/16, etc. And we could say that this is 1/2 to the n. But does it have to be 1/16? No, it could be 1/15. And that formula would end up being 6 divided by n plus 1 times the quantity of n squared minus n plus 6. And just to have some fun with it, I made another one and said I can make it any number I want. I'm going to make it 3/10. And that formula is 7x cubed divided by 240 minus 9x squared divided by 80 minus 7x over 60 plus 7/10. So what we're doing when we do this, when you write that nth term, you're assuming that the pattern continues. So be aware of that. We're assuming that pattern continues. When we look and we see that there's only 3 terms, 3 terms are not much. Four or 5 terms is better. All right, so this next part, I would strongly recommend you turn off the video, do them, because I'm just going to run through them. All right, assuming you've done that. Common difference is 4, so this is 4n, and the 0th term would be 3, or you could also say 4 plus what is 7, since it's a linear sequence. Over here, I'm multiplying by -3 every time, so I could say that this is 4 times -3 to the n minus 1. Or, more standard to write for what we're doing is we're going to have that -1 out in front. So we'll have -1 to the n minus 1 times 4 times 3 to the n minus 1. Another way to do it when you have an alternating sequence like this is to ignore the positive and negative and just say 4, 12, 36, 108 and say, what's that formula? I'm multiplying by 3, so it's 4 times 3 to the n minus 1. Now, we're going to deal with the positive and negative. So we're just going to tack on a -1, and we have to just figure out, do we want it to the n or n minus 1? And it could also be n plus 1. It doesn't really matter. We want the first term, we want the odd terms to be negative, so we'll make it n. So it's -1 to the n times 4 to the 3 times 4 times 3 to the n minus 1. The next one, realize that this is 2 squared, 3 squared, 4 squared, etc. So it's always whatever the term number is plus 1 squared. The next one, there's multiple different ways to do it. You could say that, oh, this is multiplied by 2 every single time, and this is add 4 every time. So we could say it's 4 times 2 to the n minus 1 over 4n minus 3. Or you could realize that this first number was 2 squared, 2 cubed, 2 to the 4th, and say, what's that pattern? That is 2 to the n plus 1, and the bottom would still be the same. So we want to be able to write sequences and the formula for sequences. But that being said, our focus is going to be on whether the sequence converges or diverges. All right. So the limit of a sequence, let L be a real number. Let f be the function of a real number such that the limit as x goes to infinity of f of x equals L. If a sub n is a sequence such that f of n equals a sub n for every positive integer, then this sequence must also go to L. All right, so determine whether the following sequences converge or diverge. If it converges, find the limit. So what we're going to do is write the formula for it if we don't already have it. We'll say the limit as n goes to infinity of, that top one would be n plus 4. The bottom one is n plus 1. And you don't need to show this. You look at the ratio of the powers, so this is just 1. So this converges to 1. The next one, let's do a little bit of review for this. When we look at the limit as n goes to infinity of r to the n, if absolute value of r is less than 1, then this limit is going to equal 0. If the r equals 1, then we just have 1 to that power, and that will equal 1. And then if absolute value of r is greater than 1, this thing diverges. If r is positive, then it's going to diverge to positive infinity, and if r is negative, then it oscillates. So then when we look at this problem, the limit as n goes to infinity of 3/4 to the n. We have 3/4 is less than 1, absolute value. So then this thing goes to 0. And on the last one here, the limit as n goes to infinity of n cubed divided by 2 to the n plus 1. On this one, we know we've looked at these ones before. We have an exponential in the denominator and a polynomial in the numerator. So this thing is going to 0. And so the exponential dominates. Exponential dominates. Or, if you forgot about that, you could say it's infinity over infinity, and you can use L'Hopital's. So, either one's fine. All right, let's go on to the next page. Just some more practice. We're building up to looking at some stuff soon. And when we do this, these are going to be very common things. Limit as n goes to infinity of n plus 1 factorial over n minus 1 factorial, and we need to simplify that. And you know your factorials mean multiplied by everything, all the integers less than it. So we have n plus 1, the next one down is n, the next one down is n minus 1 all the way to 1, so we can just write that as n minus 1 factorial over n minus 1 factorial. Those reduce out, so we're looking at the limit of n squared plus n, and that's going to go to infinity as n goes to infinity. Over here we have the limit as n goes to infinity of negative 1 to the n plus 1. So I'm going to just rewrite that a little bit here, and I'm going to put it as 2n plus 1 over n minus 2. And since we have n minus 2 here, I put n greater than 2, so it doesn't blow up the fraction. So then what's happening here is this first part is going to be plus or minus 1, and the second part is going to 2. Same as before. You could say the ratio, the powers, the exponents are the same. So what's happening on this, it oscillates between negative 2 and 2, so this diverges. And on the last one, we have the limit as n goes to infinity of 2 to the n over n factorial. And again, we realize that n factorial dominates. So this gives us 0. On this one, we can't use L'Hopital's because we don't know how to take the derivative of n factorial. All right. Definition. A sequence is A sub n is bounded above, go ahead and underline that, if all terms of the sequence are less than some real number, capital M, and M is called an upper bound. So in other words, A sub n is less than or equal to M for all the values. And that should make sense. So we have some number above and it just doesn't go above it. So that's our upper bound, and all the values of our sequence are less than or equal to. It's bounded below if all terms are greater than some real number. We'll put lowercase m, a lower bound. So in other words, here, A sub n is all values of it are greater than this lower bound. And if both bounded above and below, the sequence is just called bounded. Let's take a look at some examples for this. Determine whether a sequence is bounded above, below, or both. So we're going to need to look at these sequences and check it and see if we can analyze and figure out some stuff. So we have this. We could say that this is, there's a couple ways we can go about it, but I'm going to show you one. If we divide by n to every term, I like to do it for the highest power in the denominator. So we get 2 over 1 plus 3 over n. You could also think about factoring out the n that we've done before and then reducing. This is going to be less than 2 for every value of n equals to 1 or greater, because this thing is going to make the denominator greater than 1, and when we divide that 2 by that number, we'll get a number less than 2. And then we look at the other side, and we could say 2 to the n over n plus 3 must be greater than 0 because they're all positive. And these are, again, remember that symbol is for all, n greater than or equal to 1. So then this thing is bounded. It is bounded above and below. Let's look at the next one. This one I think you'll find is pretty straightforward. If we take a look at a sketch of the graph, though, we're looking at, actually not right there, we can go, since our sequence is starting at n equals 1, and you can think of this as a large scale there, where we could say the limit as n goes to infinity of 1/2 to the n equals 0, but since we're starting at 1, is there an upper limit? Yes. So remember, we're dealing with, actually go there, the natural numbers. So the upper bound will actually be, starting at 1/2, or n equals 1 will be 1/2. So this thing is bounded above by 1/2 and below by 0, so it is bounded. Number 3, if we take a look at what this would look like, it's going to be going out here and down there. So this is unbounded. It's not bounded on either side. All right, we're going to look at the limit as n goes to infinity of n squared over n plus 1. The degree in the numerator is greater than the degree in the denominator, so this thing is going to infinity. Now let's look for if we can find something below. So we'll take a look at n squared over n plus 1. We can factor out an n in the denominator and reduce, so we'll get n over 1 plus 1 over n. So if we look at n greater than or equal to 1, we have 1 if n is 1, it's 1 over a half. If n is 2, it's 2 over 1 and a half. So these numbers are getting bigger. The denominator is getting smaller. The numerator is getting bigger. This thing is going to be greater than or equal to 1/2 for all n greater than or equal to 1. And so therefore this thing will be bounded below. So it's not bounded above because it's going to infinity. All right. If a sequence, or I should say an unbounded sequence, diverges. That should make sense because if there is no number above or below, then it just keeps on going, either higher or lower. If a sequence is bounded, does it have to converge? Think about that for a second. And the answer is no. An example of that, try to come up with one yourself, would be sine of n or cosine of n. Since this oscillates, it diverges. But it is bounded by -1 and 1. All right, let's look at a monotonic sequence. A sequence is monotonic, we'll say a sub n, monotonic increasing if a sub n plus 1 is greater than or equal to a sub n for all n that are natural numbers or counting numbers. So in other words, as the sequence progresses, each number is bigger than the previous one. Its sequence is monotonic decreasing if just the opposite is true. We have a sub n plus 1 is less than or equal to a sub n. Again, each number as we're going forward is getting smaller. And we can say a sequence is strictly increasing if a sub n plus 1 is greater than a sub n, again for all n, and then it's strictly decreasing, that should say a decreasing, if a sub n plus 1 is less than a sub n. All right. How can you tell if a sequence is increasing or decreasing? We can look at the difference. So we can show that a sub n plus 1 minus a sub n is greater than 0. And if we're talking about decreasing, we would have a sub n plus 1 minus a sub n is less than 0. We could also use the ratio. If we're looking at positive values here for greater than 1, greater than or equal to 1, we can show that a sub n plus 1 divided by a sub n is greater than 1. Or if it's decreasing, we can look at a sub n plus 1 over a sub n is less than 1. So what are these both saying? We're saying here, if the difference between them is positive, that means a sub n plus 1 is greater than a sub n. Or if the ratio is greater than 1, then it's also bigger. So in other words, what both of those are saying is the next term is bigger. And it depends on the situation on which one you want to use. All right. Show that the sequence is monotonic by determining whether it's increasing or decreasing. So we're going to take a look at this one as the first one. The difference, we'll look at a sub n plus 1 minus a sub n. So that we're going to plug in n plus 1 where we have the n. So we'll have n plus 1 over n plus 1 plus 2, so n plus 3, minus n over n plus 2. Let's combine these fractions. N plus 1 times n plus 2 will be n squared plus 3n plus 2 minus n times n plus 3, n squared minus 3n, all divided by n plus 3 times n plus 2, so n squared plus 5n plus 6. When we simplify this, the n squareds go away, the 3n goes away, so we have 2 over n squared plus 5n plus 6. Since n is positive, this value will be greater than 0 for all n greater than or equal to 1. So this thing is monotonic increasing. Next one, write this note down. If there's a factorial, typically you want to use a ratio test. We're going to be doing that a lot. You can just put that there. So we have a sub n plus 1 over a sub n, and we'll have 4 to the n plus 1 over n plus 1 factorial divided by 4 to the n over n factorial. Let's simplify this. 4 to the n over n plus 1 factorial times n plus 1, or n factorial over 4 to the n. So 4 to the n plus 1 divided by 4 to the n gives us 4, and n plus 1 factorial is n plus 1 times n factorial, so the factorials will reduce. So we have 4 over n plus 1. So technically you could say for all n greater than or equal to 1, this is not going to be less than 1, but you can see as n gets bigger, once you get to 4, that this will always be less than 1. So that's what we're going to do. We'll say it's less than 1 for all n greater than or equal to 4. So we'll have a little modification here. From the fourth term on, it is monotonic decreasing, since that ratio is less than 1. All right, our last bit here. If a sequence is bounded and monotonic. So let's think about what that means. Monotonic means it's either always increasing or always decreasing. And then it's bounded. So if you have something, let's say it's always increasing, it's bounded above, that means it must be going to a number, so this thing converges. Or if it's bounded below, you can think of exponential graphs on that, then this thing must converge, and that's something we should be aware of. And that is all.